Hello, Physics 1 students, and welcome to the Prelab 2 video. Today we're going to be discussing kinematics. As you can see from the definition below, kinematics is the study of objects in motion. And so we're going to be discussing a few elementary concepts regarding objects in motion, such as acceleration, velocity, speed, distance, and displacement. So the first thing that we want to discuss is the most common type of kinematics equations that you're going to see. These are based on a quadratic position equation, which means that your object is experiencing a constant acceleration, okay? And now I specifically have the word vertical here because as you'll notice, all of these are in the y direction. On the next slide, I'll have them all broken down in the x direction. But of course, we know that the y-axis is the vertical axis, so that's why I have constant vertical acceleration. And indeed, when we work with free fall next week, these are the equations we're going to be working with, right? Because free fall only takes place in the vertical plane. So the first equation we have is the position as a function of time. So what that means is that if I plug in a t-value, so let's just say, for example, I want to know what the position is at time is equal to 2 seconds. If I plug in 2 seconds, so everywhere I see t, I plug in 2, then I will be able to calculate what the position of the object is after 2 seconds into the motion. Velocity as a function of time will do the same thing, but for velocity. So this is going to tell me what my velocity in the y direction is at any given time. I do the same thing. If I wanted to know what the velocity is after 2 seconds of motion, I would plug in 2 everywhere I see t, and that would tell me what the instantaneous velocity is at t is equal to 2 seconds. Now, last but not least, my acceleration as a function of time. As we mentioned up here, it's constant, right? So you can see on the right-hand side of the equation, there's no t. So it doesn't matter when I am, it is always going to be the same acceleration, right? Because that's what constant means. It means it doesn't change, right? So no matter when I am going to have the exact same acceleration. So before we leave this slide, I just want to make sure that everybody understands what each of these terms means. So AY is the acceleration in the vertical or the y direction. You can see it here, here, and here, okay? VOY, this is the initial velocity in the vertical or the y direction, and you can see that term here and here. And then the initial position, so in the case of a vertical initial position, that's going to be our starting height, okay? And you can see that up here. So now, as promised, we have the same kinematic equations, but this time this object is experiencing a constant horizontal acceleration. So now we are in the x direction for all three of these. So same exact equations, just everywhere that you saw y on the previous slide, you're going to see x, okay? On this slide, we're going to discuss two really important kinematics quantities. Those are distance and speed, okay? As you can see here, both distance and speed are scalar quantities, which means they're only concerned with the magnitude, which is not to be confused with a vector quantity, which would be concerned with both the magnitude and the direction, okay? So what do I mean by the magnitude? I mean whatever value you have, take the absolute value of it. Okay, and you can see right here in our equation for distance, that's exactly what we're doing, right? So for distance, if you want to calculate it, you take the absolute value of your final position. If we come over here and look at it on the graph, that would be this guy right here. If we trace a line across, that would be approximately 0.4, right? We're going to subtract our turn position. Okay, so that's going to be this guy up here. The way that you can find it if you have a data table is going to be, it's going to be the point that has the maximum displacement. Okay, so it's going to be farthest away from where you started. And it's also the place where the direction of the motion changes. Which again, if you're looking at a data table, is going to be where you can see here, these values are getting bigger and bigger and bigger, right? And then you get to your maximum displacement, and then the values are getting smaller and smaller, okay? The second half of this distance equation takes the absolute value of the initial position, so that's this guy, probably about 0.4 again, minus x turn, which is just above 0.7, right? And then you would add those two quantities together, and that would give you the distance. Now, in order to find speed, you want to take the distance divided by the time. Okay, so if we expand the distance equation like we have up here, that would look like this. And then we would divide by the time interval. So that would be t final minus t initial. So on the graph, that would be just shy of 0.6 minus 0, right? Now that brings me to a really important point. So in this example, I'm saying that t initial and t final, they're encompassing the whole graph that we have here, right? But you'll notice when you take quizzes and exams that t initial and t final do not necessarily span the entire graph, or if you're given a data table, they may not be the entire time segment given on the data table. So please, please, please pay careful attention to what your time interval is. Whenever I'm doing problems like this, I always circle what my time interval is. That way I can't mess that up when I really get excited and I'm working the problem, okay? Another thing that could be tricky is trying to figure out which term goes with which term. So you can see here, distance and speed go together, okay? Not to be confused with displacement and velocity, which go together, okay? If you happen to know the song The Distance by Cake, it's an excellent song, so if you don't know it, I highly recommend listening to it. But the chorus of this song goes, he's going the distance, he's going for speed. So all you need to know is those lyrics, and you'll be able to remember that distance and speed go together. All right, moving on to velocity and displacement. So both velocity and displacement are vector quantities. So vector quantities, as I mentioned before, means that we are concerned with both magnitude and direction. So in order to calculate displacement, it's a lot simpler than distance. We're just going to take what our final position is, and we're going to subtract our initial position. So on this graph here, you can see our final position is about 0.4. Our initial position is also about 0.4. So we're going to find that our displacement after the motion is approximately 0. Now remember, if it were a quiz or an exam, I might think to mix this up, and I might say that my initial time is over here, right? So that would put my initial position at a higher number, right? And so I would actually have gone backwards the way that I've defined this, because I would be having 0.4 minus 0.5, right? So then I would end up with a minus 0.1. So just keep that in the back of your mind. Really pay attention to those time intervals. I cannot stress that enough. Now, there are two types of velocity that we're going to discuss today, but the one that we're going to talk about first is average velocity. So the way that you calculate average velocity is your displacement divided by your time interval, or x final minus x initial divided by t final minus t initial. Or in other words, your change in position over your change in time. And if it helps you remember that velociraptor is equal to displaced raptor over time raptor. I have seen this written as distance raptor, which, as you all know now, is not correct. So feel free to correct people when they're presenting misinformation. So as you can see, I'm not telling you to do anything that I wouldn't do. This is a post from some random girl that I went to high school with, and you can see that she posted velociraptor is equal to distance raptor over time raptor. Me, a physics adjunct, I couldn't let this stand, even though I never talked to this girl ever, and I don't even really know who she is anymore. But I commented, displacement raptor divided by time raptor, because it's important. Velociraptor is a vector quantity, right? Distance raptor is a scalar quantity. We want displaced raptor. So you may be thinking to yourself, oh, you're just one of those argumentative people on the internet, but you would never say this to your friends in real life. Well, I actually would say this to my friends in real life. And by real life, I mean on the Facebooks and on the interwebs. So this right here is a meme that one of my friends posted on my wall. And of course, you can see it's the same meme with the same glaring error. And so I couldn't resist. I had to make sure that I fixed it by adding the Directoraptor. So please, be good humans and spread true and accurate information. So let's once again talk about average velocity. On the next slide, we're going to talk about the other velocity, which is instantaneous velocity. But average velocity is when your time is significant, okay? So this means you have a big time interval, all right? And you can see, finally, I'm giving you an example where the time interval does not represent the entire graph, right? So I'm saying that t initial is here and that t final is here. So as we discussed on the previous slide, to find the average velocity, you need to take the final position minus the initial position divided by the final time minus the initial time. Okay, so this would be our final position. Okay, I'm going to subtract my initial position, and then I'm going to do the same thing with the denominator but with the time. So I'm going to take my final time and I'm going to subtract my initial time. So you can see essentially what we're doing here is we're finding the slope of the line passing through t initial, x initial, and t final, x final, right? You can see that's the line right here, and we're just finding the slope of it. That's what average velocity is. It's your change in your position over your change in time, which you can see your position is on the y-axis and your time is on the x-axis. So essentially, y2 minus y1, x2 minus x1. Rise over run. Your change in y over your change in x. Average velocity is simply a slope, which represents how the position is changing as a function of time. So the second type of velocity that you may need to calculate is the instantaneous velocity. And an instantaneous velocity is exactly what it sounds like. So it means that your time interval is insignificant. So if you're given a problem, it may be worded something like, what is the velocity at t is equal to 5 seconds? Now there are two ways to find the instantaneous velocity, and which method you use depends on which information you're provided. So the first method I'm going to go over is if you're given a graph like this one, okay? In that case, you're going to draw a tangent line, and just to be clear, a tangent line is a straight line or plane that touches a curve or curved surface at one point, but it doesn't cross it at any other point, okay? So it only touches it right at t instantaneous, which in the example I was saying was at t is equal to 5, okay? So it only touches the curve at that point, but then it continues on, right? So my job is to find 2 points that lie along that tangent line, and then I want to calculate the slope of that tangent line, okay? The way that I would do that, you can see here, to calculate the instantaneous, I'm going to take xa minus xb over ta minus tb, right? This is just a simple slope calculation, y2 minus y1 over x2 minus x1, okay? When I find the slope, that gives me what my instantaneous velocity is for a graph, okay? So graphical information. If I'm given an equation, the way that I would solve it would be different, okay? So if they give me the Vy of t equation, I'm going to plug in whatever t instantaneous is, right? So say it was 5, I would plug in 5. Everywhere I see t on the right-hand side of the equation, so most likely it's just going to be at plus your constant, which will be your initial velocity. So I would just plug in 5 over here, and then I would calculate what my instantaneous velocity is that way. And that's pretty much it. That's calculating instantaneous velocity. Now, one thing I did want to mention about calculating the instantaneous velocity with the first method, so when you're given a graph, is that if you draw your tangent line, say point C is exactly the time that I was given, so that is where I want to figure out my instantaneous velocity. I can draw a tangent line, and I can pick A and B that are on the same side of the point, right? I didn't put A down here this time, and it doesn't matter because the slope of a line is constant. So as long as these 2 points lie along that line, the slope is going to be the same. All right, last but not least, we're going to discuss acceleration, and acceleration is the rate of change of the velocity. Okay, so as you can see, a very familiar looking slope equation, except this time we don't have positions in the numerator, we have velocities because that's what's changing for acceleration. So we have v final minus v initial over t final minus t initial. So a few things to keep in mind when you're considering acceleration is when your object's velocity and acceleration are in the same direction, it could be either positive or negative, then the speed/velocity of the object is increasing with time. If the object's velocity and acceleration are in opposite directions, the speed and velocity of the objects are decreasing with time. And this kind of goes with the first point, but a negative acceleration does not necessarily mean the object is slowing down, because remember, it could be either positive or negative. So if the acceleration and velocity are both negative, then the object is speeding up in the negative direction. So that's all I have for acceleration. Let's move along to the pre-lab practice problems. So before the pre-lab practice problems, this is just a summary of all the equations that we went over. You might find it handy to take a screenshot of it just so that you have them, but you'll notice when I get into the pre-labs, I usually provide the equation that you're going to be using. One last side note, vector notation is denoted by a little arrow above your vector quantity. Now, I may forget sometimes to put my little arrow above, but that never means that a vector quantity is no longer a vector quantity, okay? So if you have a force, if you have a displacement, if you have a velocity, if you have an acceleration, those are always going to be vector quantities, whether I remember to put the arrow above it or not. So without further ado, here are the Prelab 2 practice problems. Hopefully you've already worked on these, so these will all be really familiar and they'll be review. If you haven't worked through these problems already, I would highly recommend that you pause the video right now and you work your way through them and then double check your work with the video that follows this. All right, Prelab practice problem number 1. What is the distance traveled by the train between 0 and 6 seconds? Now, I cannot emphasize enough how important it is to pay attention to your time interval. Now, as I mentioned, for the examples, just so we don't confuse anybody, we are going to be using the whole time interval, but please pay attention to the time interval when you're taking the quiz and taking your exams, because it will not necessarily span the entire interval. Done beating a dead horse. So the first thing that we want to find is we want to find what our final position is. Okay, so that's over here. If we draw a line to intersect with the y-axis, we find that x final is about 25 meters. Now we want to find x turn. Okay, so in order to do that, we find the place where our direction is changing, okay, our maximum displacement, and that is at 30 meters. The last thing that we need in order to find the distance is the initial position, and that is 10 meters, as we can see from the graph. So we take all of these values, we plug them into our handy-dandy position equation right up here, okay? And we find that distance is equal to 25 minus 30, right? So x final minus x turn, plus the absolute value of 10 minus 30, or x initial minus x turn, okay? Then we simplify that, so then we have the absolute value of -5 plus -20. Then we add those values together. 5 plus 20 is 25 meters, and that is our final answer. All right, Prelab practice problem number 2. What is the displacement of the train between 0 and 6 seconds? So you can see I bolded and underlined my interval because as I mentioned, sometimes when you're taking the quiz and the exam, they will go ahead and change the interval on you. So you want to make sure you're always paying attention to what that time interval is. All right, so for displacement, that equation was x final minus x initial, so our final position minus our initial position. So just review from the previous slide, x final was 25 meters, x initial was 10 meters. So our displacement is 25 minus 10, which is equal to 15 meters. Prelab practice problem number 3. Once again, I have bolded and underlined the time interval. Yes, we're working with the same one, but I cannot stress enough how important it is to pay attention to that time interval. Okay, so in order to find the average speed of the train between 0 and 6 seconds, we are going to take the distance and divide it by the time. Okay, so the distance, as we found in problem number 1, that was 25 meters, and the time interval is 0 to 6 seconds, so T final is 6 minus 0, that's T initial. That simplifies to just 25 meters over 6 seconds, which simplifies to 4.17 meters per second, and that is the final answer. All right, pre-lab practice problem number 4. Once again, we have the same time interval. This time, we're going to be calculating the average velocity for that same time interval. Okay, so to calculate average velocity, that is the displacement over the time interval, or x final minus x initial over t final minus t initial. So our displacement we calculated in problem number 2, that was 15 meters. We've already calculated our time interval in problem number 3. So we have 15 divided by 6. This simplifies to 2.5 meters per second, and that is our final answer. So pre-lab practice problem number 5 asks us, what is the instantaneous velocity of the train at 2 seconds? Okay, so since we do not have the velocity equation, we will approximate the instantaneous velocity using the graph. Okay, so to do this, we will find 2 points that lie along a line that is tangent to the graph at t is equal to 2 seconds, and we will compute the slope. Okay, so first we want to find t is equal to 2 seconds on the graph. Then we want to draw a line that's tangent to it. Then we want to find 2 points that lie along that tangent line. And then we want to figure out what the values are associated with those 2 points. So let's just call one of the points A, and it's at approximately 1, 20, and the other point is B, and that's at approximately 3, 30. So now we can move along to the computational part. So that's going to be finding the slope of these 2 points that lie along the tangent line. So yb minus ya over xb minus xa, right? Our change in y over our change in x, which in this case, right, is our position over our time. Okay, so we plug in those values. So we have 30 minus 20 over 3 minus 1, right? 30 minus 20 over 3 minus 1. That simplifies to 10 over 2, which then simplifies to 5 meters per second, and that is the answer. Our instantaneous velocity at t is equal to 2 seconds is 5 meters per second. All right, pre-lab practice problem number 6. A car has a position that can be described by x of t is equal to 20 plus 4t squared. With x in meters and t in seconds, what is the instantaneous velocity of the car at t is equal to 4 seconds? So this is the other way that we solve for instantaneous velocity. In this case, we are given the equation, right? So we're going to use method 2. All right, so I just wanted to highlight here real quick, this is our velocity equation. So that's what we're ultimately going to be using for our calculation. But first things first, here's our position equation. I'm assuming that you don't know calculus, so you won't be able to just take the first derivative of this. So we need to do this step by step. Okay? So this is our position equation, which if we assign the terms as they've been described in this word problem, that means that 1/2 axt squared is equivalent to our 4t squared term. We have no initial velocity because you can see there's no t term in here, right? So that would be 0t. Voxt is equal to 0t. And then we do have a constant, right? Our constant is 20, so our initial starting position in the horizontal is equal to 20 meters. Now to summarize that, that means our acceleration is 8 meters per second squared. If you're wondering where that came from, we know that this term here, 1/2 ax t squared, well, we know that 1/2 ax is equal to that coefficient, right? So we know that that's 4t. 1/2 ax is equal to 4. That means that ax must be equal to 8 because 1/2 times 8 is equal to 4, okay? The next term, super easy, right? We know that that's 0. We've established that. So we have no initial velocity. Then the last term is our initial position, which is 20 meters, okay? So now we're going to move on to this handy-dandy velocity equation that we were talking about, now that we've defined all of our terms. So our velocity equation is equal to ax times t plus vox. So we take our ax, which is 8, multiply it by t, and add it to vox, which we've established is 0. So in this case, our vx of t equation is just 8t plus 0t. And if you're somewhat familiar with these equations already, you can jump ahead from doing this first step here where I have the position equation and I define all of my terms, and you can just jump right into this velocity equation. But for those who are not as familiar, I wanted to make sure that everybody understood where my terms are coming from. All right, so after you have your Vx of t equation, then you want to find your instantaneous velocity, and you want to know for 4 seconds. So we're going to plug 4 seconds into our Vx of t equation. So that's 8 times 4, right, because that's where our t is, plus 0 times t, right? 0 times anything is 0. So essentially all we have here is 8 times 4, which comes out to 32 meters per second. And that is our final answer. All right, last but not least, practice problem number 7. Now again, we're given the same position equation. So a car has a position that can be described by x of t is equal to 20 plus 4t squared with x in meters and t in seconds. What is the instantaneous acceleration of the car at t is equal to 4 seconds? So I'm going to more quickly go through all of the information that we talked about. Okay, as you can see, we're going to be talking about the acceleration equation, right, because we want to know what the instantaneous acceleration is. So that's going to be this equation right here. So let's go through everything that we went through on the other slide, right? All of the information is the same, right, because they gave us the exact same position equation. This time, however, we're going to be working with the acceleration equation. So ax of t is equal to ax, right? And it's just ax because it's constant, right? So ax of t is equal to 8 because, as we established, the acceleration is equal to 8 meters per second squared. So now we want to know what the instantaneous acceleration of the car is at 4 seconds. So if we plug in 4, well, you can see on the right-hand side of the equal sign, there is no t, right? That's because the acceleration is constant. So no matter when you are, no matter what number you plug in here, you should be getting exactly the same number, which is 8 meters per second squared. So that's our final answer. The acceleration is equal to 8 meters per second squared. And that's because our position equation is a quadratic, which means that our acceleration is constant. Hopefully you found this helpful, and best of luck on quiz 2. Now on quiz 2, remember it's a little bit different from quiz 1. You're going to have 5 questions on kinematics and 5 questions on measurement uncertainty. Okay, so make sure that you are familiar with the calculations that you did in the measurement uncertainty or container construction lab from last week, okay, because you will be quizzed on it, and that will be half of the quiz this week. All right, that's all I've got, so best of luck on the quiz.